Thanks, Grace. This afternoon I'll be presenting a case study of risk-based management for Mount Gambier's stormwater recharge system, and I'd like to acknowledge my co-authors, Declan Page and Peter Dillon from CSIRO, Jeff Lawson and Dave Williamson from the Department of Environment, Water and Natural Resources, Naomi Gray from the EPA and Darryl Sexton from the City of Mount Gambier. This activity was undertaken within the Managed Aquifer Recharge and Stormwater Use Options 3.5-year research project, which was supported by the National Water Commission, CSIRO, the Goyder Institute, the City of Salisbury, the Adelaide and Mount Lofty Ranges NRM Board and United Water International. My colleagues Peter Dillon, Declan Page and Dennis Gonzalez will be presenting more of the outcomes of this project tomorrow afternoon in a stormwater management session. This activity was undertaken in close collaboration with local and state government agencies that were represented by the Blue Lake Management Committee. The report for this work will be available within the next month on the Goyder Institute website if you're interested in downloading it in full. The objective of this activity was to document a case study of risk-based management for stormwater recharge in Mount Gambier, and it's unique in that it's an example where stormwater recharge is a significant component of the drinking water supply and has been for over 100 years. So we've got an example of indirect potable reuse. The aim was to ensure protection of the Blue Lake, which is where the drinking water supply is sourced, as that drinking water supply, but also as a lake of environmental importance due to its annual colour change. The risk management plan has been developed in accordance with the National Managed Aquifer Recharge Guidelines, which were published in 2009. The full report documents the plan which addresses the 12 elements of risk management framework implemented under the National Water Quality Management Strategy, including commitment to responsible use of recycled water, system analysis and management, supporting requirements and review. The presentation today focuses really only on system analysis and management. Just a refresher on the subject area for anyone in the audience that isn't familiar with Mount Gambier and the Blue Lake. Mount Gambier is a regional city in the southeast of the state, about 450 kilometres from Adelaide, close to the Victorian border, with a population of about 26,000. The drinking water supply for Mount Gambier is from the Blue Lake, a groundwater-fed volcanic crater lake, which is also a very important tourist attraction due to the vibrant blue colour in summer. The lake's about 70 metres deep and has a surface area of 61 hectares, and rainfall in this region is about 700 millimetres a year. Now, getting to the interesting component of stormwater drainage in the city, the urban area, which is outlined here, is about 26 square kilometres, and it's divided into numerous stormwater subcatchments. There's over 400 subcatchments, and you can see the black dots on the diagram represent drainage bores. So each stormwater catchment is generally associated with one or more drainage bores that recharges stormwater directly into the unconfined aquifer underlying Mount Gambier. This practice commenced in the 1880s with hand-dug wells, really just to resolve drainage issues. They found that if they dug a hole, water drained away. In the 1940s, they began drilling wells, and it's continued to this date. The City of Mount Gambier manages the majority of those wells, as they manage about 400 drainage wells, and there's about 50 bores with private owners. There is also recharge via infiltration basins, so the more recent developments are associated with infiltration basins rather than drainage bores, but drainage bores remain as the dominant recharge mechanism. So putting some numbers around the importance of stormwater in the water balance. Due to the steep sides of the lake, it has a very small surface catchment. So precipitation accounts for about 500 megalitres per year, but that's pretty much accounted for by the evaporation losses each year. Groundwater input is around 3,500 to 4,500 megalitres per year. A withdrawal for municipal supply is a similar amount, 3,600 megalitres per year. Groundwater outflow is uncertain, but it's minimal. And stormwater discharge was estimated recently based on the average annual discharge based on rainfall in the interval 2007 to 2012 was estimated at 5,100 megalitres per year. So really just looking at those numbers, the key point is the volume of stormwater discharge is a similar order of magnitude to the withdrawal for drinking water supply and the groundwater input. So we know that stormwater recharge in this system is a very important component of the water balance, and it has been estimated that stormwater is up to 55% of the annual recharge to Blue Lake. A quick overview of the hydrogeology. The target aquifer is the unconfined Gambier limestone aquifer system, and that consists of alternating layers of limestone and marl overlying a dolomitic camelback member. Karstic features are present, and most of the drainage bores intersect the camelback member. The wells are sort of 20 to 50 metres below ground surface, and inflow to the lake is believed to be at about 40 metres below the surface, so it's consistent with flow through that camelback member. Regionally, the groundwater flows from the northeast to the southwest and discharges to the coast, but in the city area itself the hydraulic gradient's quite low, and local flow system and reversal of flow in the karstic domain can occur. Jeff Lawson recently completed his master's research where he refined the understanding of the layers in the Gambier limestone aquifer. He also identified a zone to the northwest of the lake where recharge was most likely to occur through the primary sort of fracture flow paths. In terms of risk management, transmissivities have been estimated to vary over two orders of magnitude, from 200 to 10,000 square metres a day. But when we think about risk management, the focus is not really on the average residence time or flow to the lake. We need to understand the minimum time that a potential contaminant could be residing in the aquifer. So to understand the potential for passive treatment in that system. In this work, we've adopted a range of minimum residence time of 2 to 20 years, and that was a combination of calculation based on pumping-induced flow, and also the use of environmental and applied traces in the system. Just as an aside in terms of the scope of this work, we can see here the groundwater management zones for protection of the lake. Got the lake here, a protection zone in orange, and a larger groundwater capture zone. So the water quality and quantity in Blue Lake can be affected by a number of activities. Stormwater recharge in the city is one of those. We also have diffuse recharge and activities such as leakage from on-site wastewater treatment systems. The scope of the risk-based plan that's been developed in this activity is limited to stormwater recharge within the city of Mount Gambier, its impact on the groundwater within the city, and the impact on Blue Lake. So it doesn't take into account management of other activities, but does form a model that could be applied to other activities. It's also not a drinking water plan on itself. Drinking water risk management plans are the responsibility of a drinking water supplier, and this plan ends at the lake. Managed aquifer recharge can take on many configurations. In Adelaide, we're most familiar with aquifer storage and recovery, where we inject and recover from a single well. The Managed Aquifer Recharge Guidelines talks about defines all MAR activities as comprising of 7 components that can be identified and used for management. So no matter what your MAR system looks like, you should be able to identify a capture zone, a pre-treatment mechanism, a recharge mechanism, storage, a subsurface storage, a recovery, post-treatment and end use. So for this system, we have stormwater in the city of Mount Gambier, pre-treatment being, actually I forgot to explain the triple chamber pits. There are 3 chambered pits, if I go back here. With side entry pit and a stormwater bore, somewhere in between there we have a buried 3-chambered silt trap, which is shown here, for gross pollutant removal. And that's the majority of treatment in this system. Where we've got infiltration into a cavernous feature, such as a cave garden here, there will be a continuous deflective separation device for some treatment. Recharge is predominantly drainage wells, some karst features and infiltration. We've got aquifer storage in the Gambier limestone aquifer. We've got an additional storage component in this system in that we have 6 to 10 years storage in the lake itself that could potentially provide some treatment. Recovery is extraction from the lake, and then end use is mainly reticulated drinking water supply. There are a few groundwater bores within the city that will be used for non-potable uses. So the first step was to assess the risks that stormwater recharge could pose, and this was undertaken, this is a maximal risk assessment, so considering stormwater recharge without any preventative measures in place. So it's based on land use risk assessment and also some of the existing stormwater quality data that was available from the 1980s and the early 2000s. And the Managed Aquifer Recharge Guidelines has 12 hazard categories to assess. The first 7 are relevant to human health and only. All 12 are relevant to the environment, but the first 7 are relevant only to human health. So we've got pathogens. We don't have any information on pathogens in Mount Gambier stormwater, but stormwater is known to contain pathogens and potential risk from sewer overflows. So we're saying that that's an uncertain risk to the lake as a drinking water supply, and also in protecting the aquifer and the lake's environmental values. Inorganic chemicals are a hazard, generally the metals associated with stormwater, but we also have the use of copper chrome arsenate in the area as a wood preservative, so they're identified as a high risk. The stormwater and the groundwater are both fresh, so salinity is deemed to be low or acceptable risk and doesn't need further protection. While there can be nutrients present in stormwater, they don't pose a risk to drinking water supply, but The addition of phosphorus could potentially impact on algal production in the lake, so that's marked as a risk for further protection. There's use of organic chemicals within the city, fuel storage, fuel use, dry cleaning chemicals that are considered to be risks, so that they're also flagged as high. Stormwater can be turbid, so that can interfere with disinfection of drinking water. So that is, comes as a risk to the drinking water use, but not environmental use. The source water and the lithology are low risk for radionuclides. In terms of pressure and flow rates, stormwater recharge is actually sustaining groundwater levels, so it's a positive and a very low risk activity. There is a risk through migration in fractures because it's a karst system. We can have rapid flow. Carbonate systems can be subject to dissolution of the carbonate material, but given the long-term performance of the drainage well, that was deemed to be a low risk in this system. There is a risk to groundwater dependent ecosystems, the lake itself, and it's a low energy, quite a passive drinking water supply, so it's deemed to be low risk in terms of energy and greenhouse gas considerations. So for the risk management summary, we see there's a number of the hazard groupings identified as potential hazards in this system. And in terms of managing those, we've got the option of pre-treating. There's limited option for pre-treatment before